Hello, welcome everybody to today's LinkedIn Live session. My name is John Stegman from Neo4j, and today we're going to be talking about the topic of database scalability. And just logistically, you can ask questions along the way. If we have time at the end, I'll answer a few questions. And with that, let's jump right in. Now, to start off with, we might ask ourselves the question, why do we even care about scalability in the first place when it comes to databases? And there's really three things that are going on and have been going on for as long as I can remember that are driving a need for database scalability. Well, first of all, let's define scalability. When I talk about scalability, what do I mean? I mean the ability for a database to handle increasing volumes of data, increasing numbers of users, and increasing complexity. And with that definition, uh, there's three things that are driving the need for that. Data volumes are exploding. I think we've been seeing this uh, specifically recently when it comes to generative AI and agentic AI use cases as people start storing things like vector embeddings, which tend to be large arrays of numbers and they increase the need for storing data. So our volumes are exploding in addition to just the inherent nature of capturing more data about the world and our customers and our processes and what's going on in the world. So more data. Secondly, we're getting more and more people who want to have access to that data and use that data in their applications. So just increasing numbers of users. And then finally, those workloads, the things that we're doing with the data, we're way past the days of just simply storing data and summing it up and aggregating it. We're now doing very complex things, things like pattern detection and dependency management and so forth, that are just driving the need for more and more power from our databases. So that's my definition of scalability and why, in fact, we need to be concerned about it. It's just because all the factors that are driving scalability are factors that are impacting most of us. Now, traditionally, if we looked at how databases scale, regardless of the type of a database, there's really four main approaches that databases have taken. Number one is vertical scalability. So what is vertical scalability? Vertical scalability is just running your database on bigger and bigger machines as your need for scale grows. So when you get more data, more users, more complex workloads, you throw some more memory, some more CPU, and some more disk at the problem. And there is, I'll say, a practical limit to vertical scalability because we're limited on how big of a machine we can get, whether it's in our own environment, in our own data centers, or in cloud hosted environments. There's a practical limit to how much resources we can have. But vertical scalability is a pretty easy one. We just, especially if we're in the cloud, we just swap out a virtual machine instance for a larger virtual machine instance, and we get more scalability because we have more resources. Now, in addition to vertical scalability, we also have this concept of horizontal scalability, where instead of getting bigger machines, we get more machines to attack the problem. And there's a number of ways of doing that, and I list three of them here. So the first is replication or replicas, where we create copies of the database and we scale by letting people use those copies for the workload. Now, the easiest way to do that is for those copies to be read-only, for example. And so when people need to just read data, they can connect to one of the replicas and do their work there. And in more sophisticated replication scenarios, we can also update those replicas and make sure that those replicas push all of their updates back across a clustered environment. So the replicated databases are not designed to address all three of our scalability challenges, but they particularly address the challenge with more users. As we have more machines processing queries, we can therefore inherently support more users. But in a replicated scenario, each replica, each copy, it's a full copy of the database. Now, the second approach we can do is something called federation. So what is federation? Federation is where we have multiple distinct different databases that we want to combine together. And we can combine them together by running a query across those databases where they are. In other words, we don't need to take those databases and physically combine them onto a single server, but we can just query them through some kind of a virtualization or federation layer that lets us scale without having to do physical combination. Now, this primarily helps us with more data, right? Because we still have those individual databases running on the individual machines, but we're now bringing more data together uh, to address the need for data scalability. Then the final approach, which is in some ways the most complex of the horizontal scaling approaches, is something we'll call a distributed approach. And there, what we do is we take our data and we break it up somehow into multiple pieces and spread those across multiple servers. Now, these pieces, sometimes we call them partitions, sometimes we call them shards. I'm going to be using the term shards as we go through the presentation today to talk about them. So what we do is we take our database, we break it up into multiple shards, and then spread it out among multiple machines. Now, what that does is it enables us to support more users because we have more resources running the database in terms of more machines, but we can also run more data in a distributed environment because each of the shards is just a portion of the data in a database. And so uh, as we bring more machines to that cluster that we distributed across, we can now we can have more data because we have more space and more memory and more CPUs spread out around those multiple machines. So those are the four common approaches that databases use to scale. Now I want to talk about how Neo4j scales uh, with respect to these four categories. So first of all, vertical scalability. This, as I said, this is probably the easiest way to scale. Vertical scalability, again, is just using larger machines. Now, Neo4j supports in AuraDB, which is our hosted, fully managed database service. You can see up to 96 CPUs and half of a terabyte of RAM, which is a pretty large machine. And that's literally, as you see here, just a matter of picking the instance size that you're looking for. For those self-hosted customers who are looking to do the same thing, it's fully under your control. You can create as large of a machine or virtual machine you can create. You can run Neo4j Enterprise Edition on that, and we can consume those resources. Now, as an example of one of our customers who's doing this, you can actually go out to our case studies. There's a link here in the presentation. You can just Google for Neo4j case studies done in Bradstreet. They're running a very large database that tracks information on over half a million, no, half of a billion worldwide global businesses. And what that translates to in terms of things that are stored in the database, you could see some statistics here, well over 1.5 billion nodes in the database and 1.4 billion relationships. And they're doing that using purely vertical scalability. So they're running on quite a large AuraDB instance that lets them scale up the volume of the data in a single database. So that's vertical scalability, and that's something that has been a part of Neo4j for basically since Neo4j was invented. Now, if we switch to horizontal scalability, we talk about three approaches, so replicated, federated, and distributed. And I want to talk about each of these in detail to talk about how we do them. But basically, just to refresh the memory, replicated is putting the graph on multiple machines, or the database on multiple machines. And essentially, the whole database is on each machine. And so that on those replicas or the copies of the database, we can run read workloads. Federated is where we have distinct databases, two or more, and then we run queries across those databases. So companies that might be using a graph database for different use cases, such as maybe supply chain management and managing bill of materials or a parts database in two separate databases. But we need to combine those together in query. Maybe we're trying to do inventory forecasting by bringing in supply chain information. And so we can do that without combining physically the databases by aggregating across them. And then finally, the distributed approach, where I'm going to be announcing some really cool new architecture from Neo4j that lets us take our graph data and break it apart into multiple pieces or pieces or shards as we call them, and run those across many machines. So let's look at each of those and how we do those. So the first, when we talk about replicated, in Neo4j 5, we introduced this concept called autonomous clustering, and clustering has been around since version, I think 3 or 4. I'm not exactly sure which version it came in, but version 5 announced this feature called autonomous clustering. Now, what is autonomous clustering? Autonomous clustering lets us scale database replicas up and down based on demand. So we could do it in response to changes in demand or changes in scalability needs, where let's say for the weekend we're going to do a bunch of batch processing, so we need to create some new read replicas, and then when the week comes around again, we need to remove them, or we can just do it as a matter of growth over time. Today maybe we need 1 read replica, and tomorrow we need 2, and then a year from now we need 3 or 4. And the idea is autonomous clustering helps us manage that environment in a very simple, straightforward way. We don't need to think about, okay, which database instance and which replica runs on which machine in the cluster. When our cluster grows, and how do we rebalance? Autonomous clustering takes care of all of that for us and allows us to run those replicas across a cluster of machines without a lot of administrative overhead. In the Aura environment, the Aura DB environment, which again is our hosted, fully managed environment, it's basically a single click. If you want more replicas for your database, you just pull down on the drop down and say, well, I'd like 2 more replicas or 3 more replicas. And with a single click and a confirmation, that automatically happens. And another benefit that comes from autonomous clustering is the concept of high availability and consistency across the entire cluster. So if let's say you've got your primary instance running on one server and that server goes down, or the cloud service provider loses an availability zone that is hosting that and it's now gone, autonomous clustering will automatically detect that and automatically promote one of the other instances to become the primary, make sure that another read replica is stood up to replace the one that's now been promoted to the primary. All of that happens transparently under the covers. So in addition to scalability, autonomous clustering gives us other benefits, such as high availability, failover, and so forth. So autonomous clustering, again, is a way to implement the replicated strategy. So we take the database, automatically replicate it across multiple machines, and transparently route queries that are doing just reads to those replicas. So very simple, easy to manage, and gives us the ability to scale to more users across the cluster. Now, the second approach is the federated approach. Remember, federated is when we have multiple distinct databases that are separate from each other, and we want to run a query across them. So the example I used at the beginning was I've got a parts graph or bill of materials graph and a supply chain graph, and they're on separate databases, and I want to query across them. So the architecture or the technology we use in Neo4j is called Neo4j Fabric. It allows us to run federated queries across multiple independent databases. Now remember, we're running across the databases. We're not doing ETL to combine the databases or moving data around. We simply create this virtual database that we call a composite database. It doesn't store any actual data, it just stores metadata. And then through querying that composite database, that composite database can reach out to the members of that composite database, which are those separate individual databases that we want to run queries across. Now, Fabric was introduced, I believe, in release 5 of Neo4j, maybe version 4. My history is not too great in my mind right now, but it's been around for some time. It's not a new capability. And one of the things to note about Fabric is that when you write a query against a composite database, it looks a little different than writing a query against the individual database. So you're still using Cipher, but you need to specify where the data actually comes from, because remember, the composite database itself does not hold any of the data. So you need to modify your application a little bit if you're going to use a Fabric solution. But the benefits that you get is that you now have federated access. You might be using Neo4j databases for multiple use cases in your organization. You can now combine data together in a single query, in a single application, without needing to move data around. All right, so we've talked about vertical scalability. We've talked about replicated horizontal scalability, talked about federated horizontal scalability. Now comes the really exciting part where I'm going to introduce something. Neo4j is introducing something brand new for distributed scalability, and that something is called Infinigraph. Now, what is Infinigraph? Infinigraph is an architecture for doing distributed scalability in a Neo4j graph database. And let me just take a quick step back. Sharding or doing distributed processing in a graph database is by its very nature, complicated. You might even say tricky to do properly. And why is that the case? Well, remember, one of the benefits, the key benefits of a graph database is that we capture not just data, but we capture the context of that data. We capture the connections, we capture the relationships, and we give you a way to query across those connections and relationships very, very, very quickly. And as soon as we start talking about breaking data up, well, one of the inherent risks of breaking data up is that we're now have the potential to break up those relationships or break up those connections and break that high speed performance that we had come to anticipate or expect from a graph database. And what makes Infinigraph really special and really powerful is that we've solved that problem. And let me explain how we've solved that problem. One of the key features of the Infinigraph architecture is something that we call property sharding. So what is property sharding and how does it work? So remember, a shard is just a piece of the database itself. Now, what we've done with property sharding is we have two types of shard. One type of shard is called the graph shard. And the graph shard in an Infinigraph architected database has the entire structure, the entire topology of the graph maintained in that single shard. So what we've done in that graph shard is we have not broken up any relationships. We've not broken any connections. We maintain the ability to do rapid traversals of those relationships and connections and to query across them at scale and at speed. We've maintained the ability to do that because we don't need to traverse shards in order to connect two nodes together, because all of those connections and the relationships are stored in the graph shard. Now, the other type of shard that we have is what we call a property shard. So remember, in a property graph like Neo4j, we have nodes, which are the things in our database. We have relationships, which connect the things together. And then both nodes and relationships can have properties. So those properties, let's say if we have a person node, it might have properties such as name and birth date and tax identifier and address and so forth. For relationships, we might have, let's say, person knows that has a knows relationship to another person, and maybe that knows relationship has a start date, and maybe it has a other properties like an end date or some other descriptive information on there. Another type of a property will be things like vector embeddings. So if we have maybe a product node and we have a product description, we might also have a vector embedding that's computed by an LLM for that product description. And remember, those things can get really, really large. So what we've done is the property shards uh, contain information about the properties for nodes and relationship for some portion of the graph. And we do that essentially randomly. So for a given node, uh, we compute some identifier to tell us, okay, that's going to go on shard A or shard B or shard C, and that node's properties and all of the relationships that originate from that node, all of its properties are stored in that individual property shard. So what that does is it allows us to distribute the data, the size of the data across multiple machines in a cluster. And as you can see from the diagram here, this is based on and built upon autonomous clustering. So all of the things that autonomous clustering can do, such as distribute databases and shards across multiple machines automatically and handle failover and making sure that we have replicas for high availability, replicas for read scalability. All of that capability is here in Infinigraph because we built on the tried and tested autonomous clustering feature. And we've added the ability to now shard the properties across multiple machines in that cluster. Now, the really cool part of this is that it's fully compatible and fully transparent with all of the ways that you would access a Neo4j database. So with drivers, the connectors, the Cypher query language, the same query that you would write against a single instance database just running on a single machine, no sharding, no clustering, nothing going on. It's the same query that you'll run against a database that's deployed with the Infinigraph architecture for horizontal scalability. So you don't need to change your application at all. Now, why is that important? Well, first of all, is as you start with the use case and then your need for scale grows, maybe you have more data, you have more users, your complexity of the workload that you're running grows. All of a sudden you say, yesterday I was fine with a single instance, but today I really need to horizontally scale and I want to move to property sharding. You can do that simply at the database level by changing the topology of your database cluster, how you deploy it, as opposed to going in and rewriting your application to change how that works. So that is a really key feature here. We've made Infinigraph work the same way as single instance Neo4j works from the perspective of the developer. And what this can do is, instead of needing to or bumping up against that limit of vertical scalability that we talked about, where we have practical limits on how much memory we can get on a single machine. We no longer need to worry about that because we can now distribute across multiple machines, and essentially we're pooling together resources, memory, CPU, and storage from multiple machines to run that database. And that's really, really exciting that we can build in that horizontal scalability in such a way that you don't need to alter your database applications. And the queries stay the same, the application stays the same. And of course, these techniques can be combined. I'm sure some of you are thinking, well, wait a minute, because we have Fabric. So for example, let's say I have a database that's deployed with Infinigraph, and I have another database that's a single instance, and I want to query across those two with Fabric. Can I do that? Absolutely, I can, because the property sharding and Infinigraph architecture is transparent to the query. So I can still write my Fabric queries and have them go across a property sharded instance and a non-sharded instance. I could do the same thing with autonomous clustering. Let's say I wanted to have all of my property shards to have 10 read replicas to get just massive, extreme scalability because I have so many users, I can do that because it's built on autonomous clustering. I can do the same thing with the graph shard, by the way. Yeah, I want to deploy those shards across multiple data centers to deal with high availability and to have things automatically fail over. I can do that with Infinigraph. So Infinigraph, the new architecture from Neo4j, is enabling our customers to to get extreme scalability. I mean, hundreds of terabytes and more of data in a single graph database while still achieving the performance that you come to expect from a graph database like Neo4j. So the benefits, I think I've summarized most of these, high data volumes, 100 terabytes plus, fully ACID compliant. So you can run transactional and operational apps where you need to be sure that your data is being updated safely and consistently across the entire cluster, and all of the shards are kept in sync. It's simple because you don't need to worry about changing your application, and it supports all the tools that you would come to expect. Now, uh, explicitly, I just want to call out generative AI types of applications and agentic AI types of applications where you're storing vector embeddings, whether that's text embeddings or you're storing graph embeddings, which is type of embedding that captures information about the structure of the graph. Remember, vectors can get quite large in terms of storage. Infinigraph supports all of those kinds of properties to be sharded across the cluster. And doing things like parallel querying of the indexes are natively integrated into the architecture. So if you want to read more about Neo4j scalability, I've got the URL here. You can jump out to our scalability page and read more about uh, what we're doing in terms of bringing addressing the problems of scale to our customers. And remember, just the three things that we're addressing with scale: more data, more users, and more complexity in how we use that data. So just checking the time, we've got just a few short minutes here. Let me check a couple of questions and see if we have time to answer them. Okay, the first one's a good one. So how does Infinigraph differ from what other graph databases are doing with respect to sharding? I know of a couple of other graph databases that tout their sharding or parallel processing approach, and they generally take one of two approaches. One approach that they take is to physically break up the graph by storing individual nodes on different shards. And usually the outgoing relationships for those nodes are stored on the same shard with the node. So what's the downside of that? Well, the downside of that is I've literally broken up the structure of my graph. Remember, I talked about the trickiness or the difficulty in doing sharding with graphs is that if you break up the nodes and the relationships, you're kind of breaking up your graph. You're kind of breaking up the reason to have a graph database in the first place. You're obliterating one of the benefits. And so breaking up the graph that way, where you take nodes and put them on different shards and making relationship traversals have to cross shards, it hurts performance. And it forces developers to really think about their sharding strategy, and in terms of saying, well, I want to try to keep these nodes together on this shard. So you have to sit down and think about your sharding key. How do I shard? And you lose some of the flexibility of doing that automatically, as Neo4j does with Infinigraph. Now, another graph database that I'm aware of takes a similar approach, but they shard based on relationships. And I could say, the same thing about that approach as I could say about the node-based sharding, is that it's breaking up the structure of your graph, and you lose the benefit of having a single shard that contains your entire graph topology or the entire structure of your graph, as Neo4j does. Let's do one more question really quickly. Let's see, how about this one? When should I use Infinigraph slash property sharding versus fabric or autonomous clustering in Neo4j. I think there's one very clear indicator where you would use Infinigraph or property sharding versus fabric or versus autonomous clustering or replicated. And that is when the size of your database is starting to get to be too big to fit on a single machine. So if it's too big to fit on a single machine, okay, your vertical scalability, you're kind of at the cap there. Uh, in terms of fabric, well, it's a single database, so fabric doesn't come into play there. And replicating, you can replicate large databases just like you can replicate small databases. But if you hit that limit on what you can do in a single machine, replication really isn't going to help you store more data because you've reached that limit, as we've said. So to me, that's probably the one key thing I would look at in making that decision. And that is to say, if your database is starting to get to be too large in terms of size of data to fit comfortably on a single machine, or it's beginning to be too expensive to run those really large virtual machines or physical machines for that matter, Infinigraph is definitely something you should look at. So with that, we've reached our 30 minutes. I want to thank you for attending, and I hope that you are as excited about Infinigraph as I am. Thank you very much. Bye-bye.